Okay, let's move on to look at another common approach for performing black box optimization. This is from the general family of genetic algorithms. So let's just quickly define in a high level genetic algorithms and then dive specifically to CMAES, the algorithm that I would like to present. So in genetic algorithm, we generate m parameter vectors, right, that we're going to sample from the true function. Then we're going to select from this generation, this set of m parameter vectors, the best performing individuals, okay, vectors. The one that resulted in the highest value for our objective function. If we're trying to maximize, of course, else if we're trying to minimize it, we'll just choose those with the lowest values. So next we're going to set parameter vector with the best fitness. And this also might apply, so the best fitness out of the previous generation. In some cases we consider just the previous generation, but in many cases we also consider all of the previous generations, or just the two last generations. There are many variants. Okay, but the main idea here is that we produce several instances, individuals, let's say samples, and we examine those that perform best with respect to the objective function, and we use them to generate the next generation of samples through recombination and mutation on these set of best performing individuals from our previous generation. Okay, what is recombination? Recombination is where we take two parents, two previously good observations, good samples that we collected, and we somehow mix them together. Okay, so for instance, this can be done on the bit level of each one of these samples, and then the offspring is some combination of the two parents, or we can do it on more than two parents. Mutation is when we take a good fitting individual and we maybe flip one of their bits, right, randomly. So that would be mutating a single observation. And of course we repeat the process in several generations, and we hope to improve the sampled values over time through generations. And of course there are many variants of genetic algorithms and many ways to approach this general process by answering various questions like how many parents should we consider in each generation to be the fittest of the previous generation, how many offsprings should we produce for each generation, what should be the crossover technique or the recombination technique, what should be the mutation technique or how to perform that, and finally how to deal with continuous spaces. And that's actually a simple one to address. We'll see this in a second. So let's consider the general evolutional strategy that is commonly used, or the parameterized evolutionary strategy, and I'll explain these parameters. And we can change these parameters and get different performance. Of course, these parameters should be optimized per domain. What are these parameters? So I'll explain it through the chart flow. So we initialize some first generation, and this will be a population of mu individuals. Right, this is the mu here. Next, we're going to do recombination by considering raw. This is the raw from here. Raw fittest parents, the best parents. And we'll recombine these parents either in a weighted way, where we not only combine everything uniformly from the set of fittest parents, but we also differentiate between the more fitting parents and the less fitting parents within the fittest pool of individuals, of samples. So this can be either weighted or uniform. You can see these here. You choose either I or W. And we produce lambda offsprings. Okay, and this is the lambda here. So we explained about everything except the plus or comma. Should we use plus or comma? So this defines if we're selecting the next population of individual mu from current generation. If it's from the current generation, we use the comma, or current plus the previous generation and united with the previous generation, and then we use the plus. Okay, so there are a lot of moving parts here. Meta hyperparameters that should be optimized per domain. One thing to notice is that if we're using comma selection, then of course lambda should be greater than mu, else we won't be able to select the next population from the lambda offspring, right? Obviously. Some intuition as to how to set this, specifically the comma versus plus selection. So this is from some old papers saying that while the comma selection is recommended for unbounded search spaces, the plus selection should be used in discrete finite size search spaces, for instance in combinatorial optimization problems. So this is just a general rule of thumb. For the other values, I guess it requires some hyperparameter tuning and trial and error. With trial and error. Okay, let's now address the issue with continuous spaces. How do we do recombination in continuous spaces? So it shouldn't be a problem, right? So the x value for any parameter value, the ith parameter for the offspring, should be some either weighted or unweighted mean over the group of fittest individuals, right? The raw group. That shouldn't be a problem. How do we mutate? Well, for every offspring, we sample each parameters from the variance of the values provided by the raw best fittest individuals. I'll show you an example in a second. So here's an example. So let's assume that we're using 3/3W, this weighted, then comma 8 offspring evolutional strategy. So we're selecting the 3 fittest parents from the group of values here. So by the way, this example shows you a 2D optimization. So you have 2 values to optimize, the x-axis and the y-axis, and the value in each one of these samples. So each one of these samples, for instance, these samples represents x1 to be 0, x2 to be 0, right? The x and y are both 0, both of our tunable parameters, and the objective function returns 1. That's the value that the fitness, right? So let's select the 3 fittest parents, and let's assume that we're doing minimization. Okay, so the 3 fittest parents should be 2, 1, and 1. Right, that's the lowest values. And let's now do weighted recombination for our fittest group, so the group of size 3. So first of all, we need to compute the mean for each dimension and the variance for each dimension. Okay, so let's do it for one. So what would be the mean for x1? Let's say that this is x1 and this is x2. So what is the mean of x1? Help me out.
0.
Minus 1, 0, 1. Yes, but no. Yes, if we would use uniform, not uniform weights. But we're doing a weighted version, right? So it should be a bit higher than 1, right? So we'll have, so these are
minus 1/3 for the bottom.
So these are double weighted, the first two, so we'll have 2 times 1 plus 2 times 0, 2 times 1 plus 2.
Minus 1/3.
2 times 0 plus minus 1 times 1. Right, so it's a minimization problem, so it's upside down, and we'll divide this by 5, right, all of the weights. So this should give you 0.2, right? 0.2. Oh. Okay, and of course, M2, the mean of X2 is the same. You can see that it's symmetrical. And we can easily compute the variance. Right, this is a sample-based variant, and the equation for a sample-based variance is provided here. And we compute all of these values for the 3 fittest individuals. And now we obtain the normal distribution with some mean and some variance for each one of our dimensions, for each one of the tunable parameters. In this case, both of them have a mean of 0.2 and a variance of 0.7. Okay, now we're going to use these values in order to generate 8 offsprings. Good, sounds good, right? Let's do it. What went wrong? Right, so you can see that indeed each one of these values came from those. X1 was normally distributed around 0.2, same goes to X2, but we didn't take into account the codependency between X1 and X2, right? So variance is not enough. How can we capture codependency?
Covariance.
With a covariance, right. So the covariance matrix, we'll have to train that. Indeed, the covariance matrix allows us to capture dependencies between the dimensions, the different tunable parameters. And it allows us to enforce such dependencies when spawning the offsprings, right? So now we're going to create our next generation from a multivariate Gaussian. Okay, so let's try again. So as before, we'll set the mean as a vector of 0.2, right, for each one of our dimensions. But now we're going to populate a covariance matrix following this equation here for each one of the values. And of course, this is a duplicate around the middle line, right, around the diagonal, so you don't have to compute all ij pairs. Yes, question.
So when you're calculating the variance and covariance, we use the weighted mean, not the uniform mean, right? We use M.
Yes, the weighted mean. If it's W, then you use the weighted mean. Mm-hmm. If it's I, then you use the uniform.
Okay, while calculating variance also.
Variance also, yes, okay. Yes. You also want to take that into account. Okay, so now we have a multivariate Gaussian. And what will happen if we'll create 8 offsprings now? It looks better, right? Okay. This looks much better, and of course this shows you that you have to take the covariance matrix into account to account for the dependencies between the dimensions that you're optimizing. What about the step size? So now when we update the mean and the covariant matrix between generations, we don't want to set the mean and the covariance as just following the current generation, but we actually want to update it over time to have something more like an exponential moving average. Just because if we just set it to some far location, we might end up oscillating between values, right? We might oscillate between the optimal point and never convergent. In order to do that, we call them as gradient steps, but it's not really a gradient, right? It's just steps towards the optimum. And so we're going to update the means and covariance with some step size. How do we set the step size? So of course we don't want it to be too big, or even just jump to the next point, as I said before, because that might oscillate, or if we take too big of a step, so we don't want it to be too big, because then we'll have to just go back and we'll see our gradient taking us back to the place that we were previously. That tells us usually that we're diverging. our step sizes are too big. We don't want it to be too small in the sense that we're performing several gradients in the same direction. So we know that we could just take a bigger step and then avoid several generations. Just get to the correct general direction of the optimal location. Finally, we would like some reasonable step size that allows us to save on generations while not taking us to a wrong direction, to a wrong location. So the main idea here is that if we see several updates that go in the same or a similar direction, then we increase the step size. We can have it dynamically set. And this is something that we've seen before, right, when we discussed momentum in gradient descent. Well, this is something very similar. So let's see an example of how covariance CMAES would work on training a control function for cars. Right? You might say, well, this is a differentiable function. I know that this is just optimized, assuming it's not differentiable, just as a black box optimizer, right? The control function. And you can see here several generations at each episode. The blue cars are the fittest out of each generation, and they are considered as the parents of the next generation, the raw. And okay, indeed, after sufficient generations, it will be able to complete the track. And of course, a reinforcement learning agent, if we assume that the control function is differentiable, would do it probably quicker. But this is a nice demonstration where even if you consider the control function as a black box, you can still train it pretty effectively. Yep. Okay. We're able to complete the track. Good job. Okay, so let's see a quick comparison between the two approaches that we've seen so far, the finite difference approach and CMAES. So the finite difference approach would be let's say this green rectangle around our current point in blue, representing the extra samples that we perform around, right, with this randomly plus epsilon or minus epsilon around our current point. And we'll use these samples in order to approximate the gradient around our current point. This is considered an approach that performs less exploration compared to CMAES that tends to spread out. However, it's considered safer. Specifically, it will perform more stably. Right? Each sample is more similar to they're more similar to each other, each one of our samples. But it has a harder time escaping local minima because it's more dependent on the local gradient, which we know has problems escaping local minima. CMAES, on the other hand, performs more exploration compared to finite difference approach. It's considered less safe, of course, and it has an easier job escaping local minima. And we can see here how CMAES starts with some first generation in iteration 1. And the fittest individuals from the first iteration pulls the Gaussian, the multivariant Gaussian, towards the more promising direction, and so goes in iteration number 3. And eventually, though, the fittest individuals do converge on the correct optimum. Okay, and you can see how the finite difference approach does perform smaller steps towards, indeed, the more conservative steps towards the optimal point. Now, it might seem from these results that a finite difference approach performs better. Or the benefits of it outweigh the issues with CMAES, but I'll tell you the truth. In most cases, as you saw in our previous publication, in interesting spaces, non-convex, high-dimensional, In most cases that I saw, CMA-ES is a very powerful black box optimizer. In most cases, it outperforms. Find a different approach.